You can restart. Yes, hello. No technical difficulties were had. So mapping. What is mapping? It's the way that we encode information about the environment around us and record it for future use. So you need this for path planning and navigation because the robot needs to know where it's able to go and where it's not able to go. There are a few common ways to store maps. One way is through occupancy grids, which is the way to basically you have a rectangle or a grid of cells that are squares, and each cell contains information. And then there's quad trees, which is sort of a recursive method of mapping the world. And we'll talk about them more now. So an occupancy grid. So this is one way to tell where obstacles are in the world. There's a bunch of cells, and each one contains some information on if it's occupied, empty, or unexplored. And these are usually a 2D or 3D array. So it contains information either as a grid, or you can sometimes have 3D ones, which have a lot more information. So in real applications, we rarely know if something is actually occupied. So we have this thing for confidence. So we don't say there's an obstacle here. We say we're confident there's an obstacle here. And so here's a few examples of things. So like 0 would mean we're fairly confident there is no obstacle here. A 1 means there could be an obstacle here, but very unlikely. 9 and 8 mean we're very confident there's an obstacle here, avoid this. And then usually the value of -1 is for unknown. So we don't know if there's an obstacle here because our sensors haven't reached that yet. So it's important to differentiate between, we know there's no obstacle here and we don't know anything. And so the library that you use for this with ROS is CostMap2D. And so a cost map is a variant of a occupancy grid where each cell has a cost in it. And so this is used for path planning. And the path wants the smallest cost possible while also, having the cost of a path is some combination of the sum of all the cells it goes through and the length of it, and maybe some other factors. But basically, this is a way of saying you don't want to go through red. Like the path planner will not go through red, and it'll try to not go through blue. And I'll explain a bit more in the next slides. So there's multiple ranges of cell costs, and there's this scary picture on the side, but it's basically there's lethal costs, which means that the robot is sitting on top. It means that if the robot were on that position, it'd be sitting on top of an obstacle, which is unideal. So that's what these red spots are. These are where we've detected there is an obstacle. Inscribed cost means that the robot is close enough that its inscribed circle, which is like basically the size of the robot, it would be inside that obstacle. So the robot doesn't necessarily have to be on top of a cell cost to have on top of an obstacle to have a collision. It can be close enough that it is colliding with the obstacle. So inscribed is also bad. There's circumscribed, which means that it's close enough that there's a possible collision, because not all robots are perfect circles. So you have this sort of pentagon-shaped robot, and this is the inscribed circle. This is the circumscribed circle. So if there was an obstacle like where my mouse cursor is right now, there would be no collision, but it's hard for the cost map to say exactly what the cost would be if the robot were here, unless it knew the exact orientation of the robot, which it can't. So it just says, try not to go near here. Try not to go close enough that you get inside the circumscribed circle. There's this range of not free space, but it's not an obstacle. So basically this would be like, don't try not to go through here, but it's not lethal. It's not bad if you go through it. So like maybe you have an algorithm which like makes it so that steep slopes have a slightly higher cost than completely flat ground. The robot could go up that slope, but if there's an option to not go through it, then the robot will choose not to. There's free space, which is a bit obvious. It's no cost at all to go through it. So that means there's no obstacles, no problem with the robot going through it. And then again, unknown is usually -1. Or in this case, because it ranges from, it's like an unsigned int, it would be 255, which is -1 in some contexts. And so to construct a cost map, the main way you do it is through the concept of layers. And so each, there's a master cost map, which is made up of multiple layers, and each layer handles a different aspect. So in this case, this is just taking from the IGVC code. We have a line layer, which detects lines and puts them on the cost map. A traversability layer, which detects like obstacles the robot can't traverse over, which is its own layer. There's this concept of the inflation layer, which is handling this whole inscribed and circumscribed thing. So it's all this blue. And then the global cost map, which is all of that combined. And so it's a way to like separate the work on making a cost map so everything isn't super complicated. And then we talked about confidence earlier. So like how confident a robot is in a cell being unoccupied or occupied. And one way to do this is through the Logit function, which is this thing on the right. So it's this sigmoid graph where it starts out, its bottom value is 0, its top value is 1. So we're confident there is nothing here, and we're confident that there is something here. And so every time like an obstacle is detected, it ticks up here, and then every time it's not detected, it ticks back down. And so this is a way of the robot to build confidence in the thing. So if it keeps like seeing an obstacle like but then not seeing it, it'll like flow back and forth here and just stay at like 50% because it's unsure. But then if it sees it more and more, it will become fully confident that there is an obstacle there. And then likewise, if it sees there's nothing there, it'll say there's 0% chance that there's an obstacle there. And so there's some scary math to like actually calculate the constants in this case, but ROS has some built-in functions to do all that math, so it's all good. But yeah. And then outside of ROSMap's CostMap 2D stuff, which is like the official library, there's some other useful libraries for elevation, because like a cost map isn't a very good way of just like storing map information because it just has those costs. So one library is such as a grid map, which gives you a more complex map object to store data. So like this is an example of like what a grid map can store. So like it has height and stuff. And one functionality is that you can actually like filter through them. So you can search the map for features. So say you have this elevation map here. You can find the steepness of the things. So you see that this blue means that it's completely flat, red means it's fully steep, and then you have this like it's like I think it's a dome. So it's flat at the top and then steep at the edges. And you can get interesting information through using grid maps. And so overall, with an occupancy grid, it's easy to visualize. It's fast to search. It's just basically an array. So it takes no time it takes little to no time no matter what size it is. And it's fast to add obstacles. It's quick to say, there's an obstacle there. I'm becoming more confident that it's there. The cons, it is, as you might expect for a very large array, expensive in terms of memory. And so a 50 meter by 50 meter space with 10 meter or 10 centimeter resolution. So like each cell is 10 centimeters by 10 centimeters would have 250,000 cells or 0.25 megabytes. So quite large. If you have a 3D occupancy grid, it's a lot more expensive because you're dealing with 3D arrays. And they don't, no matter, like they have a low resolution because of this expensive in terms of memory issue. Because if we went down to like 1 centimeter, this thing would multiply by 100. And so you'd have 25 megabytes, which is bad. And now Andrew will take over to talk about quad trees.
Should I share or
guess? You can just tell me when to next slide.
Okay. Then so for quad trees, they're an alternative to occupancy grids. So we start with a map that's divided into large cells. Similarly, like very similar to a quad tree, to an occupancy grid. But when we see an obstacle, we mark all cells completely in the obstacle as occupied. And if the obstacle only occupies part of the cell, we subdivide that cell into 4. And then we repeat this process essentially for each of those inner 4 cells. And then what this allows you to do is you'll end up having a lot more small cells around the edges of obstacles, but large areas can be also captured by like larger cells. So you're no longer like limited to a single cell size for all your cells. And yeah, you can see here in this picture, you have some obstacles which are marked in black. And when you add them to a quad tree, what you end up having is these very large cells that store information about it being either occupied or not occupied, but then also around the edges, you get a much finer resolution. And this leads to a lot better use of memory because you can store very large areas as big cells, and that obviously doesn't take a lot of memory. And then where you care about the resolution, which is around the edges of obstacles, you get much finer resolution. So next slide. Yeah, so to achieve this, a quad tree uses a tree structure, and often this is done using an array in the back, like as a backing structure, but it's still a tree. And the pros of this method is that you get it is a lot more memory efficient, and you generally, because of that, you can go to higher resolutions. So like last time we said 10 centimeter, like you might be able to go down to 1 centimeter and still use the same amount of memory as a occupancy grid. However, the cons is that it's longer computation time for adding and searching cells. So instead of being able to directly like use O of 1, just go to directly to the cell that you care about. Since it's a tree, you have to actually traverse the tree, and that's typically log of n, so it's a little more expensive. It's still relatively cheap if it's a balanced tree, but yeah, that's the main con. Other types of maps. So we really only talk about grid-based maps, and that's because they're the easiest to navigate. They're usually used for path planning because each cell essentially has there's a notion of whether a cell is area is occupied, which is what we want for path planning. But there's also other types of maps, such as feature-based maps and topological maps. So feature-based maps, they store a bunch of landmark locations. And as we'll see, this is actually really useful for SLAM, and which we'll talk about right after this. And then there's topological maps, which have nodes and their interconnections. And those are very efficient, but they can lack in they can be a little hard to apply to robotics. But yeah, those are the main three types of maps that you might see. So SLAM, SLAM stands for Simultaneous Localization and Mapping, and it basically is what it what it sounds like. And in this picture, you can see that you have some actual positions of your robot, but you're also tracking some sort of feature or obstacle, whatever you want to call it. And you don't know the exact position of those obstacles. So you actually have to estimate your position and the location of those features at the same time. So next slide. So yeah, up to this point, we've talked about localization and mapping as two separate problems. So in localization, which I talked about 2 weeks ago, it was all about finding the location of the robot, assuming we have a known map. And then we had mapping, which we covered today, which assumes the location of the robot is known. And we're just mapping where the obstacles are. And this works really well for simple cases where we're localizing from a subset of sensors, such as a GPS, IMU, odometry, and then we're mapping obstacles using other sensors, such as cameras and LiDAR. But sometimes you want to use the data from the cameras and LiDAR and the location of the obstacles that it's finding to actually get your location. And when that happens, this method of separating the two doesn't work quite as well. So because you have to estimate the position of the features you're looking at the same time as your position, because those two are linked now. So next slide. Yeah. So if we want to localize off these features, we need a way to estimate both the robot position and the position of the features. And for this, we're going to use some SLAM approaches. So we already actually know one technique, and that's Kalman filters. So if two weeks ago, I covered Kalman filters, and we had the state vector, which was essentially that defined the state of the robot. And it used to be just like the position of the robot, so like x, y, theta, and then we might even include velocity in there and angular velocity. But now what we're going to do is just add the obstacles as additional state variables. So you can see that the state now also consists of the position of obstacle 1 and the position of obstacle 2. And as you can imagine, this ends up being a very large state vector, because here we have two obstacles. In real life, if you're say trying to track points in the camera image as you're moving, that might be thousands of obstacles, or thousands of features. And so this state vector is going to be thousands of variables long. And also typically we'll use an extended Kalman filter for this, not a regular Kalman filter, since the robot itself is going to be nonlinear, the dynamics of the robot. So if we do that with a Kalman filter, what we see is this essentially what this GIF is showing on the right. This is a GIF of a robot traveling in a circle, and each of those points that are not like the red points are certain features that it's tracking, and it's trying to figure out its position relative to those features. And the circles indicate the uncertainty of the position estimate. So, for example, as you can see, as it travels, the position estimates get more and more uncertain until it actually comes back full circle. And when it comes back full circle, that's called loop closure. What's happening here is the robot sees a feature that it has seen earlier on. And as it's moving, its uncertainty grows because the location of the features are, well, the first time it sees it, it just assumes that it's somewhere like offset from the position of the robot. But as the robot's traversing, we know that it gets, we're losing information and the position of the robot gets more and more uncertain. So the position of the features it's adding are getting more and more uncertain as well. But when it comes back to a full circle, it sees a feature that it saw when it was more certain about its position. And so what it can do is it can propagate that back. And essentially, you'll see as soon as it finishes the circle, all the uncertainties of the obstacles and the position all reduce greatly. Like the circles essentially all shrink. So yeah, that's called loop closure, and that's one of the benefits of using SLAM. So next slide. Yeah, and in practice, using Kalman filters for SLAM is, if we're just going to use like regular extended Kalman filters, is extremely inefficient. And it's not to say that it's not done ever, but it's pretty inefficient. Like earlier experiments with it, people would like track about like 200 features, which sounds like a lot of features, but it's really not in terms of what we do today. And the main reason it's so inefficient is because that state vector will grow really large. And if you remember, if the state vector is n variables long, then the covariance matrix is going to be n by n, which means you're going to have a giant matrix. If it's 1,000, if your matrix is, well, if your state vector is 1,000 variables long, your matrix is going to be 1,000 by 1,000. And so you're going to be tracking 1,000,000 values. And there for Kalman filters, we have to invert that covariance matrix, which is a really expensive operation. It's n cubed. So that's the main reason that it's like not super used. But one thing that people have done is they sparsify the covariance matrix, which means that whenever the covariance is close to 0, they just set it to 0. And this actually can make it a lot more efficient. Mainly because the algorithms used to invert the matrix can be designed to take advantage of sparse matrices and can perform the task much more efficiently. And by nature, SLAM problems tend to be sparse because you can only see a certain subset of obstacle or features at a single time. So I guess next slide. Yeah. So a more like modern technique for doing this is using factor graphs to represent the system, and then using nonlinear optimizers to minimize the error. So on the left we have a robot. Essentially, it has 3 states: x1, x2, and x3, and at each state it's sensing something about the environment. So it has a sensor measurement, Z1, Z2, and Z3. So this might be, for example, a GPS measurement of its position. And what we're trying to figure out whenever we're doing localization is, given these 3 sensor measurements, what are the positions at x1, x2, and x3? And this can be represented as a factor graph. Essentially, it's the like you can tell that would be it would be proportional to the probability of where it is in x, what's the probability that it's at x2 given that it was at x, and then probability x3, and like that would be the probability that it's at x1, x2, and x3 given those sensor measurements. Yeah, go to the next slide. Yeah, so when we represent it as a factor graph, what we're going to do is every unknown variable that we're trying to solve for, So this might be the locations of the features or the robot position. We're going to mark them as a circle with, and they're going to be an unknown variable that we're trying to solve for. And each black square represents a function that that essentially, it can be any, for factor graphs, it can be any function. For us specifically, it's going to be the probability essentially that we're getting the sensor measurements when we're at state X, given like a state X. What we're trying to maximize is the product of all these functions. So each of these black squares would be essentially a function. And whatever it's connected to are the variables that go into that function, or unknown variables that go into that function. So like sensors, as you can see, they actually are kind of built into the function. But these unknown variables of like where we're located when that sensor measurement was taken, that is an unknown variable, and so it's represented by the circles. So yeah, the bottom left black square is connected to x1, which means it only depends on x1. It doesn't depend on x2 or x3. Yeah, so our goal is to maximize the product of essentially all these functions, all 6 of them. So go to the next slide, I think. Yeah, and so factor graphs give a representation that we can optimize, and because it's a graph, it's very easy to tell which unknown variables are linked to which functions, and this allows us to use optimizers. And the reason I don't specify any specific optimizer is because you can actually use a lot of different ones, and even just for any of these packages below, you can choose between like 3 or 4 different optimizers. And that's actually a benefit of using factor graphs, is that it's very flexible. You can also use nonlinear models, which, if you remember with Kalman filters, we could do with extended Kalman filter, and it achieves a similar way. Actually, factor graphs, like the optimizers, typically linearize as well, but that's still an advantage of factor graphs. And then also a big advantage is it can use incremental solvers. So, well, to optimize these unknown variables. And what that means is that you don't have to restart each time when you're trying to solve for the for all the positions. You already kind of know your position from last time, and then you get new evidence. So you just want to optimize the few positions, like say like 10 seconds ago. You don't really. It's not like seeing a measurement now won't indicate that your measurement 10 hours ago was wrong. So by using incremental solvers, you can actually compute both the position and the position of the features in real time. So it's very efficient. And there's two frameworks. Well, there's many more frameworks than two, but two frameworks that do help you design and create these factor graphs and then optimize them is G2O and GTSAM. And GTSAM is actually from Georgia Tech, so yeah, that's basically all I have to say for that. And this is like what an actual path might look like. So the blue dots would be the entire path, and then the well, I guess they're both blue. The cyan dots are the path, and then the dark blue are the features. And as you can see, it's only linked to certain features at certain positions. So when it's at the end, for example, it's not linked to those first few features, and that's captured by the factor graph because the unknown variables they won't be linked to factors later on if they're not actually like seen from that position. Yeah. So next slide. I think I have a video. Yeah. So can you skip to like, I think it's like a minute in.
Does this need audio?
No, this does not need audio.
Cool.
So if you can skip to a minute in or so, like I think it's, yeah, that's fine right there too. Just showing what you can achieve essentially. So there's actually the Leo SAM that's on the right. It's actually using GT SAM and factor graphs, but essentially, you can see that they're building a map and localizing at the same time, and they're building a pretty good map. Yeah, that's mainly it. I mean, there's they're tracking the point. They're using the point cloud to essentially add measurements into to track their position, because this is using only IMU and LiDAR. So there's no GPS measurement in this one.
Discrepancies between the three different versions.
Yeah, and there's going to be a lot of different SLAM like versions out there, but yeah, you can see that like on the left, for example, like if you didn't correct, it would be even worse. This is actually slightly correcting. So if you were just using IMU measurements, your map would look terrible. But you can see on the right that by using SLAM, you can actually correct and get much more like square edges, which is what you expect from a map like this. And I guess, yeah, later on in some points of the video, they have they show loop closure, which is kind of nice. But
I think it's this video, I'm pretty sure.
Yeah, so here they're injecting GPS measurements. This is just because it's a very large map, and there will be still drift because SLAM, like, it helps, but there's still always drift in sensors. So I think this is the zoomed in portion.
Yeah, it's zoomed in the center.
Yeah, so gaps. Yeah, so because of drift, you can see that there is a big gap there. But then when the loop is closed, it essentially fixes that gap, and it'll realign all the points before it in order to try to position the features over each other. Yeah, so that's the main two advantages of using SLAM, is that you get loop closure, and also like it's kind of like not an option if you're trying to track off of features, like your position off of features, because you don't know where the features are and you don't know where you are, so you have to find both at the same time. So yeah, I think the other ones are basically the same thing, but the other video. But yeah, so I think that's it. Yeah, that's it for today, I guess. It's a little shorter than normal, which is good. Any questions? I know we covered everything pretty high level, but it's because it would take a while to cover it fully, like a lot longer than an hour.
I don't see questions.
Yeah, no questions. So I guess, Kyle, what do we want to do now?
All right, so hold on, let me stop the recording.